SwayamPrabha. Digital India. Educated India.
Hello everyone, welcome to NPTEL course on groundwater hydrology and management, week 1, lecture 3. The previous lectures, we looked at how and why groundwater is very important in the hydrological cycle. Then we focused on the different aspects in groundwater use between developing and underdeveloping nations, how groundwater is being used especially in underdeveloped and developing nations for agricultural activities. We then also looked into the disparity in water use, which is leading to a disparity in water stress. And we also looked at within India, the water stress is leading to further depletion of groundwater. Okay. In today's lecture, we will look more deeper into the hydrological cycle. We would also bring some concepts from the Central Groundwater Board in assessing the water stress. Let's understand the hydrogeologic process for groundwater. What we see here is the hydrological cycle overall with a mass balance or a water balance, which shows how much water is available as an example for a particular area, and how the different water sources are contributing to the atmosphere and then coming back as rainfall. Okay, you could see that evaporation from the oceans is contributing 320,000 kilometer cube water to the total water, which is 380. So big portion of water does come from your oceans, whereas evaporation also comes from your mountains and freshwater resources like your lakes, rivers, etc. And it comes back again as some amount of rainfall, okay, which we have here around 96 kilometer, 1,000 kilometer cube as rainfall along the slopes and on direct onto the ocean, because ocean has a bigger space in area. So on top of the ocean, there's a good rainfall event also, 284,000 kilometer cube, right? So if you add them, it goes to 380,000 kilometer cube, which is the total. Of the 96, some goes as runoff, okay, and some is converted into infiltration through your recharge activities into the ground. The water can come back into the oceans or small freshwater bodies or rivers, lakes, etc., and then eventually flow to the ocean. Lake water, ponds, etc., need not flow back. It can be evaporated, but those which also go in the deep aquifers or deep groundwater paths eventually go to the oceans. So now what constitutes groundwater? Is it a different source of water? No, it is coming from the same precipitation atmospheric process. Either it can be from snow converted into water. So snow is kind of a solid phase, and then ice melting, etc. So once they melt, it's called snow melt. And that snow melt can come down from high elevations into rivers, water storage systems such as ponds, lakes, and aquifers, right? And they can come down into the ground through infiltration. So infiltration is the process by infiltrating water into the soil. It can move further as groundwater component. So what are the different sources? Atmospheric precipitation that infiltrates into the ground is the key source. And of the atmospheric precipitation, rainfall is the key source. There's multiple different ways in which precipitation can happen. One is snow, hail, sleet, drizzle, etc., dew. But we will focus on rainfall more because the rainfall process is easier to understand the flow into the rivers, lakes, etc., and you can also relate it directly to your infiltration. Surface water that becomes trapped in pore space of sediments during the deposition in lakes, streams, and especially the oceans is also a source for groundwater, which means suppose you have a lake, suddenly it can be trapped by some debris. For example, you have an erosion. A lot of sand is going to be deposited on top of a lake. What happens? Your water is pushed down, or the water gets locked in the system. Once the water gets locked, it cannot move anywhere. Either it constitutes or comes back to the other groundwater sources by further pressure, or it stays there as a perched water table. So some surface water body can be stored. Water degas from cooling magmas, which means your lava material is there. When lava flows, a hot molten material, magma, when it flows, it can also degas, and water is a byproduct. So that water can be stored in your rocks and sediment as a groundwater source. And then there are some metaformic reactions that break down into hydroxide minerals. So the point here is we are not focusing on the deep water, groundwaters, resources, etc., because that is not what we use and what we can manage. The only management option is don't take that water, right? You don't do fracturing to take that water. So we will focus more on the water that is annually used, for example, groundwater for drinking water, etc., so that you could better manage the resource. So this course would be focusing on the hydrogeological process and the groundwater hydrology up to the confined or deep aquifers, not very deep aquifers, just to the deep aquifers, which are being used and exploited for agriculture, for industries, and urban demand, urban and also rural domestic demand. So that would be our focus for this course. Let's look in a pictorial diagram of what constitutes groundwater. And in here you have the stars as snow, and snow can convert into surface runoff, which is easier explained using the rainfall. So rainfall can hit the surface and convert into surface runoff. So water is hitting, water hits, it goes as surface runoff. Okay. So water you see pooling, floods, all those are discharge or surface runoff due to rainfall. Okay, let's start from the clouds. You have precipitation. Precipitation can fall on the ground. Part of it or most of it can go as surface runoff. It depends on the land use. If you have urban centers, houses, etc., most of the water goes off. Whereas if you have agricultural land or a forested land for a good part, then water can infiltrate. Water infiltrates and goes into the root zone. So you can see here, water first infiltrates. While runoff also it can infiltrate. While on the river, while in a pond, lake, water can infiltrate. So it just needs extra time. Okay, it's much slower compared to the surface runoff process. So when there is a slope, so this is your land, a slope, water is falling. As soon as water falls, most of the water goes as runoff and very little water goes down as infiltration. And that is because the infiltration rate is much slower than the precipitation rate and or the surface runoff discharge, or the process that contribute to surface runoff. Moving on, after infiltration, some water goes in. The infiltration can come from stream flow, surface runoff, precipitation, and or stored water bodies like here. So once it goes in, it hits the root zone. The first part is you have your soil, the top surface, water goes in. The top part is organic matter and humus, etc., which is okay. But then when it goes in, it goes as a root zone. That is where the plants have their roots extended and it can easily take the water up, the groundwater. After the root zone, you have the tree root zone. Okay, there's a plant root zone, there's a tree root zone. Both are not the same, just a depth difference. Okay, but you can combine both of them as a general root zone. So the water can go into the root zone after the plant has taken it up, after the reallocation of water has been done subsurface in the lateral direction. So this is vertical. and this is horizontal or lateral. So water moves vertically, and then it can go spread out laterally also, and then can continue to go down. Why is it going down? It's because of gravity. So gravity is the force which is responsible for the groundwater hydrology component. It drives the system. Otherwise, water can just go up, right, from precipitation. It comes down because of gravity. It hits, infiltrates because of gravity, etc. And once in the surface, subsurface also inside the soil, water will move down to the root zone because of gravity, not just because of the plant's pulling capacity. Okay, so once water moves to the root zone, some soil would be taking up the water, depends on the properties of the soil, and some plants would be taking up the water. At least plants would take it up and evapotranspiration happens, whereas your soil just stores the water. It's called soil moisture. Then we have the subsoils. The subsoils is when you have a soil layer below the root zone where water can also enter. So some part of the infiltrated water will go into the subsoils. And that is where percolation happens. Percolation is further movement of water or relocation of water under the subsurface. And then you have your bedrock and aquifers. So bedrock would be your confining unit, which is impervious most of the time, but then you can have some water going through. So it's a very slow process. And then finally, it can come to your aquifer after it bypasses your root zone and subsurface soils. Okay. While you're in the root zone and subsoils, after you have crossed it, groundwater can also go laterally rather than vertical. It can move laterally because of the bedrock or the impervious surface. Okay, some water can go on the side and come out into oceans, then evaporate, go back to the rainfall and come back again. So this cycle can go on. What you see here is the remaining water after interflow, after subsurface flow, some water does enter the aquifers. The aquifer is the storage part for groundwater where a lot of porosity or space is available for the groundwater to be stored and groundwater to move. Please do not think it's like a river, like the diagram here is showing. It's just a soil material with a lot of holes, soil or rock material. It's a medium with a lot of holes where water can be stored. And if the holes are connected, water flows. We will get through each definition in the coming lectures. So percolation is the important phase where the precipitation converts into groundwater resources. Because before that, infiltration is the initial part, but most of the water can be taken up by plants or soil. It need not go down through, right? So that part we'll be very careful in understanding that only after percolation you have the concept of groundwater hydrology. And some part of this water can go up due to capillary rise. It's very, very small, but still we need to acknowledge it. So capillary rise can happen because of the nature of the soil. Water can be pulled up and stored here. Even plants can pull up, trees can pull up. Okay. And again, do not imagine this as a river flowing. There are rivers that flow under the ground, especially in caves. But groundwater per se doesn't flow like a river, but it is flowing through pores and it goes through a medium mesh of materials. It's not an empty space like your river is there. It's not an empty space where water can flow. It is with materials, and so it is very complex in nature. And groundwater will eventually join the oceans or evaporate in your local water bodies. So now you understand that compared to surface hydrology, groundwater hydrology is much more complex. You have here is all your surface hydrology components, whereas your groundwater is more complex because of the complexities in the water reaching the aquifer and also how it flows through a porous medium. It is not a river where you can put a dam and then store all the water, right? It can just bypass it because that's the way it was initially flowing. So it is a porous medium a medium with a lot of holes, be it sediments or rocks, soil, etc. And then through that, water can move. Okay. So again, why is groundwater important? Let's look at one more analysis. Groundwater makes up a large portion of Earth's hydrological budget, water budget, and it is widespread in the Earth's crust. It's not just located like the oceans are located only in some areas, not in the land. Groundwater is located everywhere. Okay, even under the oceans, you have groundwater aquifers, and that is where it might be seeping and leaking into the ocean. So 0.62% of total water budget. Compare this with the FAO, which was saying 0.69, and the other study, which was calling it 0.5%. Of the total water budget is from groundwater. Okay. So only 14.2% of Earth's fresh water is accessible. Only 14.2 of Earth's fresh water, because most of it is in glaciers, etc. The 14.2 is because some groundwater cannot be accessed. Even though groundwater can be 20%, it cannot be accessed. So in the previous exercise, we saw 2.5%, here it's 2.8%. And that 2.8%, almost 90% or 80% goes into your glaciers, and the 20% plus 1% is here. So that 21% equates to only 0.62%, and that 0.62% is also not fully used because some of the groundwater is stuck. Okay, so please understand that there is a hydrosphere, which is the hydrological budget of all the water resources, and no ocean component is this one. Okay, so because you've taken the ocean out, so you put this as 100%. All these is to drive the factor that groundwater is a high commodity compared to the fresh water available, but the stress is making it very unsustainable. And also on top of that, why is the stress there? Because the freshwater availability on the planet is very less. We've been thinking that everywhere there's water, atmosphere there's water in snow, ice, but it is such a small portion when you convert it to fresh water, and even a smaller portion when you say accessible fresh water. For example, fresh water is inside our body, but can we access it? No. We need to replenish it. So when we drink, we replenish it, because we also have a sweat and our water comes out of your pores, etc. when we transpire. So we also are like a small mini hydrological cycle. We drink water, and then we excrete water, and also we transpire water. What is it driven by? So what is all these budgets and hydrology are driven by? The first and foremost thing is your precipitation. Let's look at an isohedral map from Professor Raghunath's book. You could see that India has a unique and very different land use, land cover pattern, which enables different hydroclimatic zones. So you can have the driest of the driest regions, 25 centimeters, and one of the top precipitation regions in the world around here, Cherrapunji, etc., and along the Western Ghats. So think about 25 centimeters here, whereas you get 250 centimeters on this side, 500 centimeters on this side. Okay, so that's 5,000 millimeters of rainfall. And here along this coast, you get around 3,000 millimeters of rainfall along the Western Ghats. So that's why you have so much rain in Kerala and etc. So almost double you get here. However, here on this side, you don't even get 10% of it. Okay, so 5% of that comes in, and which is very, very less compared to how much water. So there is big differences in water availability, and this also drives the stress, and because of that, it also drives the need for a groundwater access. The other thing which it drives is, first you need rainfall to eventually recharge. The other thing is you need a material to store the water. And here the material is the hydrogeology, wherein It is the geology, the rock, the sediment, the materials where the water can store. So the groundwater is not just a unique one process. It is a combination of processes. It has to start from your rainfall, get into the soil. The soil has to have conditions to promote groundwater storage and groundwater flow, which you see from the maps here. And then water should be able to be stored. If water just flushes through, it's not groundwater, right? It just moves through and goes somewhere else. It has to be stored. Slowly, it has to be released. So if you look at here, you have good groundwater yield areas here along the Ganges, Indus, Brahmaputra, which is also regions with good, decent rainfall. It's also the Brahmaputra. Okay, and then you come to central India, where you have medium yield aquifers or yield groundwater storage units, where they have consolidated, semi-consolidated formations of rocks. And those rocks cannot store much water. And that is why you have a less yield. Yield is how much you can take out. And this part is also, if you remember the stress diagrams, this part is also the regions where high water stress is being predicted. High water stress is not predicted here because you have good rainfall and you have good potential of the aquifer to permit, store, and use the groundwater. Whereas here, you have less rainfall first, so the farmers are forced to take groundwater, and on top of it, the geology doesn't support storage of big water store units. It's very small water that you could store. Moving on, it is a combination of your geology and hydrology, and so you have a hydrogeological map. And geology is a very, very important process for groundwater movement and storage. Depending on this, there's a lot of calculations done to understand how much groundwater we have, how much is recharging, etc. And it is given in different units. We'll be using the unit billion cubic meters per year by Central Groundwater Board. I'm just giving an example. You don't have to worry about how do you calculate all this. These will be calculated in the following lectures. The idea of this slide is to zooming in, is to just show you a calculation. Let's take Madhya Pradesh, for example. It has annual replenishable groundwater resource, which means count for groundwater and it gets replenished annually. It's like your salary. Every month you get in money and you can use it throughout the month. So for example, you are getting money on the month end of the 31st, and then you use from 1 to 30, right? So you deplete it and then it gets replenished in the month end. So same way you have estimates for annual groundwater use. So these are the positives. Recharge is 28.22 BCM per year. And then you have recharge from other sources, 1.17. This could be your magmas, surface water storage, other things. But recharge of rainfall is biggest. Okay. Then you have non-monsoon recharge, which is not from rainfall, and recharge from other sources. Industries, rivers which are flowing can recharge, etc. The total comes to 35.05 billion cubic meters per year. And the natural discharge, naturally water will go into your oceans. I showed you in the hydrological diagram. So that component is very small. And if you subtract that from 35.05, you get 33.29. There are some decimals, so you would see some adjustments. So 33.29. Now this is the natural draft, natural extraction. Let's come to the human anthropogenic extraction. So for irrigation, that is the biggest use of water, 17.48 out of 33, 17.48, more than 50%, okay, is used for agriculture. And then your domestic and industrial use still not as big, but close, okay, very, very close to your natural discharge, which means your natural release of water. Then you have your total. So if you subtract all these from 33.29, you will get around 18.83, which is your net total draft. Okay, so 17.48, 135 gets you 18.83, which is your total draft. You should add this with your discharge also, or you can subtract this from 33.29. Getting that, you get a percentage of groundwater development. These two are projected groundwater use for industry. So this 1.35 can go up to 1.91. And groundwater available for future irrigation, which is the remaining part, is given here, 13.90. Either way, what you see here is the stage of groundwater development. So almost 60% of your groundwater in Madhya Pradesh is used every year. So still it's on an okay number. So they will call it semi-critical or safe. Why? Because you are getting 100 rupees, and out of the 100 rupees, only 60 you're using, the remaining 40 you're saving, like a bank account, fixed, etc. The 40 won't stay because it is a leaky account. Water will go to some other place, it moves into the oceans, etc. So under that circumstances, 60% is still okay. Okay, so the government doesn't put a cap on that value. I'll come to the image here. Okay, so you have critical over critical. So it will be around semi-critical to safe, which means not big management activities are needed at this stage. Okay, so we looked at a particular state, and I just took the top list so that we could have the titles also. Moving on, how much available water is there as per a basin size? Initially, we saw a state. State is more important because the administrative boundaries is where you can do management work. You cannot do Ganges management across different states because some states may not be accepting the same project, correct? So what happens here is we are still showing the basin wise, because basin is how the water comes through the hydrology, through the climate, weather, and also your watershed approach. So looking at that, your Ganges basin is the biggest replenishable groundwater resource, and also it uses very, very low. So that's why only 33% of the groundwater is used. So of the river basins, the Madras and Southern Region Basin, which includes the small rivers in the southern Chennai region, is highest because it's also industrial and also urban use driven groundwater depletion. The irrigation is also there, so around 60% of the water is used. So if you do a basin-wise calculation, all are safe, which is wrong, right? You cannot do that because some blocks might be within your basin. Your basin size is pretty big, and within the basin, 1 or 2 blocks can be notorious and pump all the water out. And that is where it will disrupt the system, and you need to put some controls or management activities. This is the annual replenishable groundwater resources as per the rainfall diagrams and where water can replenish. Okay, so unit recharge is up to 0.5 here and very, very less in the light blue colors. So you could see most of the Ganges, Indus Basin, Brahmaputra, all in dark blues, and along the deltas where the water, river water discharges into the ocean, you have a good dark blue color showing a recharge anywhere from 0.5 to 0.25. After that, it is pretty slow recharge rates. So we need more activities. And if you look at this image and this image, you could see clearly wherever there's a slow recharge rate and less rainfall, that is where people are actually consuming more and more groundwater. Rajasthan, Haryana, Punjab, etc., Gujarat. So, and here you have in the southern region also, Andhra, Karnataka, Tamil Nadu, some parts of Kerala also. So it is very important to understand these red color zones where immediate actions have to be taken to preserve groundwater. Red color means you are using more than your annual recharge. So if 100 rupees is coming into your account, you're using 120 rupees, which means you're using a credit card or something. So eventually you need to pay it off, right? And that is where it is marked in red. And the government is telling that we need to, kind of these images are telling, we need to take stringent actions or management activities to change the color, change it to a more critical or semi-critical stage. So with this, I would like to conclude the lecture. We have gone through how water comes into the groundwater hydrological system, and how groundwater data, this recharge estimates can be used to understand the water budgets. And then we ended up as hydrology and geology should be considered to understand the groundwater part and demand and access, etc. I'll see you in the next class. Thank you.